So we had started describing our system using a Sturm-Gerlach experiment with a magnetic field in the z direction, and we had seen that okay, basically we can describe any system to be either in one state or the other state, which we call the plus and the minus. And then we studied the other Sturm-Gerlach experiments, for example, the Sturm-Gerlach in the x direction, and we had seen that, again, this Sturm-Gerlach experiment in the x direction basically splits our systems into two different possible states, which we called Sx plus and Sx minus, and we had seen that we could write these states in terms of the plus or minus states as 1 over square root of 2 plus plus minus, and 1 over square root of 2 plus minus minus. And we had defined our operators, expectation values, etc. But basically, who told us to use the Sturm-Gerlach experiment with a magnetic field in the z direction? It was just a choice, and well, we could just have started with a Sturm-Gerlach in the x direction, labeled our states with the eigenstates of that experiment, that measurement, and we could have just done the same thing. So basically, if we use the Sturm-Gerlach experiment in the z direction, we had some basis states. Let me call them AI, which we label them by some observable, which we represent as the operator A. So the AI are eigenstates of this operator. We could have as well chose some other basis. Again, these will be some orthonormal bases. Now, the claim is we can switch between these two bases. Well, basically, that's what we did over here. We can switch from one basis to the other basis. So basically, from the plus-minus basis, we could go to the Sx plus, Sx minus basis. Now, the easiest way to see how we go from one basis to the other one is just to construct this operator. So this operator, if you take this operator, act on it with on Aj with this U operator, you will get sum over I, Bi, Ai, Aj. And this operator over here, this inner product is just 1 if I and j are equal. It is 0 otherwise. So it's Kronecker delta Ij. So when you sum over the I, you get Bj. So this operator, in a sense, maps one basis state to the other basis state. Now we can look at some more properties of this operator. Let's say U dagger. What about U dagger? Well, the U operator maps the A basis to the B basis. Now, if you calculate the U dagger operator, this is sum over I, Bi, Ai dagger. We had already discussed the properties of this dagger operation, so it basically changes the order of the operators and the bras and kets, and also converts a bra into a ket into a bra. So if you just change their place, this is AI, Bi, sum over I. So this U dagger basically maps the Bi basis to the AI basis. And this operator has also one more interesting property. Let's look at U dagger U. So what is U dagger U? Well, this is equal to sum over I, AI, Bi. This is my U dagger. U is sum over J, Bj, AI, Aj. Since the two summations are independent of each other, I just changed the dummy label. Or this is equal to sum over Ij, Ai, Bi, Bj, Aj. Well, this is nothing but Kronecker delta Ij. So this is equal to sum over I, AI, but we had seen that since AI's form a basis, this is just 1. So this matrix, this U dagger U operator, not the matrix, the operator is just the identity operator. So we have this operator U, who, when we multiply U with U dagger, and you can also show that U dagger U is also, U dagger is also 1. This is called a U is a unitary operator. Now, we will see in quantum mechanics quite often these unitary operators. The one nice property of these unitary operators is that they do not change the norms, the total probability. So if you define, for example, beta to be equal to U times alpha, where alpha is a normalized state, is equal to 1, then beta, which is, well, let me write it in this form, beta ket dagger multiplied with beta. Well, the beta ket is defined in the first line. If you take the dagger, it just means convert bras into kets, kets into pras, and switch the order of the things. So it's alpha U dagger. This is beta ket dagger. U alpha, this is my beta. This is beta ket. This is beta bra. But U dagger U is just 1. So this is equal to alpha, which is equal to 1. So what this would mean, remember this, the amplitude of a ket, we just interpret it as a probability. The total probability should be 1. It's this one over there. So that total probability is conserved under a unitary transformation. So that is something we would like to have, for example, when we are talking about time translation. So we have our ket now. When we obtain our ket in the future, it's essentially a time translation. So we don't want the probabilities to, the probability, for example, that the particle is somewhere should be 1. It should always stay 1, even under time translation. So this basically tells us that time translation should be a unitary operator. Now, we will be doing those in the future. Now, let's look at the matrices. So you see, on one, we have this ket. We had seen that we could show this ket as a column matrix. On one hand, in the alpha base, in the AI basis, this is equal to AI alpha. On the other hand, we can also show the same alpha ket in the BI basis, BI times BI alpha. So, and then we said that, okay, we can show it as alpha AI, alpha BI, A1, alpha A2, etc., or alpha B1, alpha B2, etc. Now, you see, there's one thing you have to pay attention to. These two column matrices are different. They are not the same column matrices. Nevertheless, the ket they represent is the same state, is the same ket. Although they look different, the reason why they look different is that we are using different bases. So just these numbers over here is unavoidable. They will be different, but nevertheless, they represent exactly the same thing. So then the question is, how are these related to each other? So let's look at one of them. Let's look at, for example, BI alpha. What is BI alpha? Well, this is equal to sum over J of, well, let me write it in this way. This is BI, sum over J AI. This is 1. I just inserted 1 times alpha. Well, this is equal to sum over j bi, well, these are j, aj alpha. Now what we have here is, this is the column matrix representing the kit alpha in the BI basis, whereas this is the column matrix represented the same kit in the AI basis. And they are related by this. This just looks like a matrix element. So if you just identify this as the ij element of some matrix, if you look at over here, this is the ij element, this is the j element, this is just matrix multiplication. Now what is that matrix, that operator over there? Let me write it in this form. This is sum over j bi ket dagger aj alpha sum over j. Well, bi, we define the operator u as u acting on ai, dagger aj alpha. This is equal to j ai u dagger aj alpha. Are you following? Not really, not yet. I mean, in a concrete examples we will do that, but what we are doing is we are already saying that the BI basis and AI basis, they are related through this U. That is what we are saying. And then since the bases are related, the matrix elements, matrix representation of our objects, they should also be related somehow through U. That is what we are trying to do now. And what we did was we just, okay, so this is the matrix relation, matrix representation of alpha in the BI basis. We are trying to relate it to the matrix representation of the same kit in the AI basis. So on the right-hand side, I want everything to be the AI base, to be written in terms of the AI basis. And so I can write this BI kit, or when I take the dagger, the bra, in terms of the U. So then I obtain this relation, but you see, this is nothing but the matrix element in the matrix representation of U dagger. So this is equal to sum over j U dagger, the ij element, multiplied with aj alpha. So this basically tells me that if I have this matrix representation of the kit, this is equal to U dagger multiplying alpha A1, alpha A2, etc. Or we can even go the other way around. Just multiply U on the left, on both sides. So you will get U acting on alpha B1, alpha B2. This will be equal to alpha A1, alpha A2, etc. So basically, U takes you from one basis to the other one, U dagger takes you the other way around.
listede herhangi bir değişiklik olmadı mı şimdi?
No, this, you see. Now, on one thing, U is unitarity, so it conserves probability. Okay, that is one thing. The second thing, U, this, okay, so let me look at over here. The ket alpha is the same ket. No matter which basis I use, it's the same ket. It's just like, if I have this vector, let's say, I can use x, y, and z axis to represent the components of this vector, or I can choose the x-axis to be in that direction, the y-axis to be in that direction, the z-axis to be in that direction. I can choose different coordinate axes. But the vector is still the same. The vector is independent of which basis I use. Similarly here, this ket over here is independent of which basis I use. Of course, in one basis, it will have components given by these inner products. In some other basis, it will have components given by this inner product. They will look different, just like the components of this vector will look different if you just choose different coordinate axes. But although it is the same vector, it doesn't change. Similarly, the components of this ket will look different in different bases, although the kets are the same. And the transformation between these two things is obtained by this unitary matrix U. This unitary operator U maps the representation of the same ket from one representation, from one basis to the other basis. That, okay, one interpretation of U is that it just tells you how your coordinates are, the components are transformed as you are rotating your coordinates, let's say. That is one way of looking at it. Now, we will have a different way of looking at the same thing, by the way. This is just one use of U. You can use U to convert from one representation in one basis to another representation of the same ket in another basis. That is one use of U. But we can do one more thing. As you said, U is an operator. Basically, when you act with U on any ket, it will change it. You see, here we are talking about the matrix representation of U, which we said that we can use that matrix representation to map between the matrix representations of these kets in different bases. But U is an operator. The way we defined it, this is an operator. So if you start with a basis, if you start with any ket, you see this alpha, let's say it has such an expansion, CIAI. U acting on alpha will be CI U acting on AI. This is CI BI, which is definitely not alpha. This is another use of U. U, okay, so there are these two different things. U as an operator, it does change my state. So you see, I act on alpha, I act with U, it just changes AI to BI, but since BI is a different basis, these coefficients did not change in this representation. So I obtain a different ket. This is a different ket than this one. This is one use of it. Or I can take the matrix representation of U. I can construct its matrix. In that case, I can use exactly the matrix representation of exactly the same operator to go from one representation of a ket to another representation of the same ket. That was over here. Okay, let's look at it in this way. Rotations in 3 dimensions. Okay, I have these 2 coordinate axes. I can talk about 2 different rotations. One is if you have this arbitrary vector, you can rotate that vector. Okay? This is one transformation. It doesn't change the magnitude, but you get a different vector. Okay? Any questions on this one? It is this one over here that we are doing. You have a rotation, you have one ket, one vector, I just rotate it. I get another vector which has the same magnitude. Or what I can say is that I have this vector. I can use 3 numbers to represent this vector. I choose one coordinate axis, and then I have 3 numbers, the components of this vector. I can rotate my coordinates. If I rotate my coordinates, then these 3 numbers representing my vector, I should use different 3 numbers. I cannot use the same 3 numbers.
Peki yönün eigenvalüsünü bulursam o zaman koordinatları değiştirmiş olurum ama yine aynı.
Well, let's see. Again, let's apply apply this idea to the rotations. Let's look at rotations around the z-axis. There is an eigendirection, the z direction. The eigenvalue is 1. The other ones will not be real.
Hocam o zaman öklit üzerindeki atıyorum bir transformation matrix'in yaptığı bir vektörü öldürme diyelim. Bunun magnitüdü değiştirmemesiyle burada Hilbert uzayında probability'yi değiştirmemesi aynı fiziksel nicelik mi?
Aynı mathematics, exactly the same mathematical property. Let's do the example. I will just, for simplicity, look at rotations around the z-axis. This is my vector v. This is my x-axis. This is my y-axis. My vector v, let's just assume that it's also in the xy plane. I know that it has components vx and vy. Well, I don't have to choose these coordinate axes. I could have just as well chosen this coordinate axis. Let's say this is x prime, this is y prime. And in this new coordinate axis, v will have the components vy prime and vx prime. Now v, I can write v as vx in the x direction plus vy in the y direction. Or I can write exactly the same v as vx prime in the x prime direction plus vy prime in the y prime direction. Now what is vx? Vx is v dot x hat. Just use this relation. X hat dot y hat is 0, x hat dot x hat is 1. I'm left with vx. So vx, I can write it in this form. But this is also the same vector v. So I can write, just if you substitute v over here, you would get this is equal to vx prime x prime dot x hat plus vy prime y prime hat dot x hat. This is my vx. What about my vy? This is equal to v dot y hat. This is vx prime x prime hat dot y hat plus vy prime y prime hat dot y hat. Well, I can write this as vx vy. This is equal to vx prime vy prime x hat prime dot x hat y hat prime dot x hat prime dot y hat prime dot y hat. So the components of the vector v in one coordinate axis and the other coordinate axis, they are the same. Now, they are different, Vx prime, Vy prime, Vx, Vy, but they are related through this relation. This is my operator U. So we had already said that the matrix elements of U are nothing but the scalar products of the basis vectors. Exactly the same thing happens in real space. Now, I can do one more thing. This is my V. Let's say this angle over here is theta. So here, this U just becomes, well, let's see, x hat prime dot x hat is just cosine theta. Now this matrix element, y hat prime is this vector over here, x hat is this vector over here, this angle over here is also theta, so the scalar product of y hat prime and x hat just gives me cosine pi over 2 plus theta. Well, that is minus sine theta. X prime hat dot y hat, it is this unit vector multiplied scalar product with this one. This is again theta, so this angle over here is 90 minus theta. Cosine of 90 minus theta is sine theta, cosine theta. That is our U. Now let me do another example. You see, in that example, what I did was this was my coordinate axis. I rotate my coordinate axis by an angle theta. Now this time let me rotate V by an angle theta. So let's say this whole angle is alpha. So this is my new V. Let me call it V prime. And this angle over here, let me also call it theta. So this angle is alpha minus theta. So V prime x, the x component of this new vector, will be the magnitude of V multiplied with cosine of alpha minus theta. This is equal to V times cosine alpha cosine theta plus V times sine alpha sine theta. But this is nothing but V times cosine theta is Vx, cosine alpha, times cosine theta plus Vy sine theta. This is my Vx prime. Do you agree? So what I did is V times cosine alpha is, V is this length, this is my alpha. So V times cosine alpha is this length over here, which is nothing but Vx. And I can do the same thing for the y component of my new vector. This is V times sine alpha minus theta, which is V times sine alpha cosine theta minus V times cosine alpha sine theta. But this is Vy cosine theta minus Vx sine theta. And so I can just combine them. Vx prime, Vy prime. This is equal to cosine theta sine theta minus sine theta cosine theta Vx Vy. So this is what we had obtained, and in the previous case, that was our U. Oops, sorry. No. Well, I can just invert this relation. Vx, Vy is equal to cosine theta minus sine theta, Vx prime, Vy prime. Well, basically, from our general construction, this is a unitary operator. You can check that it is a unitary operator. So its dagger, its inverse is just its dagger. Since it's real, its dagger is just a transpose. So the inverse of this one is this one. So you see here I have the Vx, Vy given by this matrix elements, Vx prime, Vy prime. Well, in the previous example, it's exactly the same thing. Now, what does this tell us? So we have this object U, which in this examples, the U basically is a rotation. Now, we can have two different views of this rotation, just like in our Hilbert space case. We can either treat this rotation as a rotation of the coordinate axis. You see, in the second example, what I did was, this was my coordinate axis. In the first example, this was my coordinate axis. Then I rotated by theta. This is what I did in the first example. You see here. Okay. So this was my coordinate axis. I just rotated it. So this one. This is a rotation. Or I can describe exactly the same rotation in this example. This is my vector v. I rotate it into v prime. Well, the one thing you have to pay attention to, in the first case, I'm rotating the axis in one direction. In the second example, I'm rotating the vector in the other direction. So these are in a sense, these are the dual roles of this U. So you can treat U this unitary transformation, unitary operator U as an operator that changes your ket. That is what we will do most of the time, is changing our ket. Or I can treat this U at least in its matrix representation. I can treat it as a way to go from one matrix representation using one basis to another matrix representation using another basis. So I can treat U as a change of basis, just like change of coordinates. So whenever whenever you are working with the unitary operators, just pay attention to which one you are doing. Are you changing your ket, your states, or are you changing your basis? Essentially, they are the same thing, but you need to do only one and not both of them. The confusion usually arises when students try to interpret one transformation acting on both kets and the basis, both on the coefficients and the kets. So the operators are acting either on the coefficients in this way. So the U is here changing my coefficients in its matrix representation, or here, U is acting on the kets itself, changing my ket. But U will not do both of them. It will either change the coefficients or it will change the ket. Now, one use of it is, let's say, we said, for example, alpha I is an eigenket of this observable A. Sorry, I call them AI. Now, AI are related to BIs through this relation. or AI is equal to U dagger BI, since U is unitary. The AI kits and the BI kits, they are related by this unitary operator U. So let's say A acting on AI is actually A U dagger acting on BI. And we know that this is equal to AI acting on U dagger BI. Well, let me multiply by U from the left. U A U dagger acting on BI is equal to AI multiplied by U dagger BI. But you see, this is just 1. So here I have another eigenvalue equation. So you see here, these BIs are some different kits than AIs, but we have an operator which is also unitary. You see, if you just take, this is Hermitian. You see, let me call that B. B dagger is equal to U A U dagger. Let us take the dagger of that. Well, the definition of dagger, switch the orders, reverse the order, take the dagger of each one. This is U A dagger, U dagger. This is U A U dagger, or B. So we have another observable. And BI is an eigenket of that observable with exactly the same eigenvalue. U A U dagger and U are called unitary equivalent observables. No, not U, sorry, A. So this is just a definition. These two observables are equivalent to each other in a sense, and they have exactly the same spectrum also. Now, one example, S6 and SZ. They are unitarily equivalent to each other. Well, this, in a sense, let's say, this degeneracy or ambiguity, let's say, whatever you would like to call, basically reflects the ambiguity in the choice of our directions. You see, X direction and Z direction, physically, they are equivalent directions. There is nothing special about the X direction. There is nothing special about the Z direction. So they are equivalent in a physical sense. In our mathematical construction, those equivalents are reflected in the fact that those two operators corresponding to, let's say, S6 and SZ, they are unitarily equivalent to each other. Do you agree? Now, in a sense, at this point, it's basically a definition, but that basic definition is a reflection of our, in general, in physics, let's say, arbitrariness in certain choices, like the axis. The choice of the axis is arbitrary. So it is reflected in this arbitrariness. That arbitrariness is reflected in having unitarily equivalent observables that have exactly the same eigenvalues, exactly the same spectrum. Of course, the eigenkets, they are different. BI ket and the AI ket, they are different, but they have exactly the same eigenvalue. Well, let's construct this operator U. We said that Sx and Sz, they are unitarily equivalent. So what is this operator U in that case? We had constructed the Sz operator that was h bar over 2 plus plus plus minus h bar over 2 minus minus. This was our Sz. Or this was h bar over 2 plus plus minus minus minus. And Sx was h bar over 2 Sx plus Sx minus minus, no, plus minus Sx minus Sx minus. And this was the Sx operator. So let's see how we had construct. So we basically need to go from this basis to this basis. Let's look at our definition of U. It's over here, the new basis and the old basis. U is equal to Sx plus plus, nope, there's no sum, plus Sx minus minus, this is my operator U. Well, I know what the explicit expression of Sx plus and Sx minus is. This is equal to 1 over square root of 2 plus plus minus plus plus 1 over square root of 2 plus minus minus multiplied with the minus product. Or this is equal to 1 over square root of 2 plus plus plus, okay, 1 over square root of plus plus plus 1 over square root of 2 minus plus plus 1 over square root of 2 plus minus plus 1 over square root of 2, no, minus 1 over square root of 2 minus minus. This is U. Well, let's see, this is 1 over square root of 2 plus plus minus minus minus plus 1 over square root of 2 minus plus plus plus minus. Or if you like, you can write this as U is equal to 1 over square root of 2, 2 over h bar Sz, that is the first one, plus 1 over square root of 2, 2 over h bar. Do you recognize the second line? No. Just a 6. So this is our operator U. Let's check. So U, A, U dagger. Now A is Sz. This is equal to, well, we have this square root of 2 over h bar squared, which is common. Then we have in U Sz plus Sx Sz And if you take the dagger, SZ dagger is SZ. Well, they are both Hermitian. SZ plus SX. If I didn't make any mistake, at least. So let's calculate what this is. This is equal to square root of 2 over h bar squared. Well, let's see. SZ times SZ times SZ. Plus SZ times SZ times SX. Plus SX times SZ times SZ. Plus SX times SZ times SX. Well, let's calculate SZ squared. So you see, in the first term I have the SZ squared, second term I have the SZ squared, the third term I have the SZ squared. Here, well, if I just exchange this one, somehow I will get SX squared, so I might be able to say something also about the SX squared. What is SZ squared? SZ was h bar over 2, well, I have two of them, plus plus, minus, minus, minus, plus, plus, minus, minus, minus. This is my SZ squared. H bar over 2 squared. So let's see. This times this. Well, plus plus is just 1. It gives me plus plus. This times this one. Well, there I have a bra plus. Here I have a ket minus. Their inner product will be 0. If I look at these two, I have the bra minus, the ket plus. Their inner product will be 0. So I get this times this. Well, minus minus makes plus. This minus sign and this minus sign makes a plus sign. So this minus bra with a minus ket is 1. So it's plus minus minus. Well, you see, this is nothing but the identity operator. So these are my eigenkets. I'm just multiplying the ket and the summing the ket bra of the eigenkets, and I'm summing over all eigenkets. This is just the identity operator. So this is equal to h bar over 2 squared times the identity operator. So u sz u dagger, this is equal to square root of 2 over h bar squared. H bar over 2 squared sz plus h bar over 2 squared sx, the first term, the second term, plus sx times h bar over 2 squared. It is this term. Well, I have to do something with that one. I need to change sz and sx. That is plus sx times a minus sx times sx sz plus sx times sx sz plus sz sx. So you see what I did over here. This is minus. That just cancels this term over here. I'm left with this one. This is the term I have on the last equation over there. So you see, this is sx. Well, just you can repeat the same derivation with, instead of using the plus and the minus kets, bra and kets, you can just use sx plus and sx minus. It's basically the same derivation. So this is also h bar over 2 squared. So this will cancel this one. So what is this? Anticommutator of Sx and Sz for spin 1/2. Do you remember? Kronecker delta. Kronecker delta of what? Kronecker delta of 1 and 3, which is 0. So this is 0. So U SZ U dagger is equal to 2 over h bar squared times, well, that is 0. Here I have the h bar squared over 4sx here, h bar squared over 4sx over here, so it's just h bar squared over 2 sx. It's just sx. So that was kind of our purpose, to show that the sx and sz was unitarily equivalent operators. And we know what u is.
İşte U, SZ, U'ya göre yaparken doğrudan SZ'i seçmeniz önemli yok değil mi? Oraya SX yapıyorsam sonuç SZ çıkacak.
A good homework question. Is it SZ or minus SZ or what? So this is homework. I mean, we will prepare the homework, write it down, but if you just want to start right away. My guess would be minus SZ. You see, what does this UU dagger operation do? Let's say if this is my x direction, this is my z direction. UU dagger operation, in a sense, in terms of the coordinates, it just converts z to x. It's a 90-degree rotation. But then x just becomes minus z. So my guess is it will be minus z. That is because we are using the u that maps sz to sx. I can find, since u, sx and sz, here we had proven that sx and sz, they are unitarily equivalent. That basically means there is a u such that it will map sz to sx. But the other way around is also true. There is a unitary operator that would map sx to sz, but that will be a different u, not this u. It will basically be u dagger. So this will tell me that sz is equal to u dagger sxu. Not u sxu dagger. So if you just use the u that maps sz to sx in here, it will not map sx to sz. It will map it to something else. My bet would be minus sz. Any questions? Well, let's give a 10-minute break, and then we can continue.